This is example 10.8, and it's entitled Calculating Power from Torque. An electric motor exerts a constant 10 Newton times meter torque on a grindstone. So which has a moment of inertia, 2 kilograms metered square about its shaft, 2.0. The system starts from rest. Find the work done by the motor in 8 seconds. So work at T equals 8.0 seconds. The grindstone's kinetic energy and the K at this time. What average power is delivered by the motor? So we need to find those three values. We need to find the work at T equals 80 seconds, kinetic energy at that time, and we need to find the average power delivered by the motor. Let's begin. Okay, so we have, we know tau, summation of tau equals I alpha. And alpha is 5 radians per second, and tau is 10 newtons meter. I mean, tau is 10 newtons times meters divided by I, which is 2.0 kg times meter squared, gives us alpha equals 5 radians per meter per second squared. All right. So we had alpha equals 5.0 radians per second squared. And now we need to find the distance. Delta theta is going to be equal to 1/2 alpha times t squared. So delta theta equals to 1/2 times 5.0 radians per second squared times t was that 5 seconds? 8 seconds. 8.0 seconds quantity squared. And that value is going to give us 160 radians. Okay, work is going to equal to tau times delta theta, which is going to be equal to 10 newtons times meters times 160 radians. And that's going to be equal to 16,000 joules. So let's see, we got work at 16,000 joules. And the delta T, let me get that, delta T equals 8.0 seconds. There's another value, alpha. I think I have all that. Let me clear my board and I'll continue. Okay, now I need to find the kinetic energy. So this is a rotating object, and that's going to be equal to 1/2 I omega squared. I need omega. So omega is going to equal to alpha times time, which is 5 radians per second squared times 8 seconds. 8 seconds. 8 seconds. And that's going to give me 40 radians per second. So now K equals 1/2 times 2.0. Oh, this is meters. 2.0 meters squared, sorry. Kg times meter squared times omega, which is 40 radians per second, and that's quantity squared. So K is going to equal 1,600 joules. And I probably didn't have to even go through that calculation if I were being astute. Anyway, let me clear my board. Now to solve for my power. Power average is going to be equal to work over time. That's 1,600 joules divided by, was that 8 seconds? 8.0 seconds. And that's going to be 200 watts. That was 10.8. 10.9. 10.9 is angular momentum and torque. And it reads, a turbine fan in a jet engine has a moment of inertia of 2.5 kilograms times meters squared. So I is going to equal to 2.5 kilograms times meters squared. About its axis of rotation. As the turbine starts up, its angular velocity is given by omega equals 40 radians per second cubed times t squared. So find the fan's angular momentum as a function of time and find its value at t equals 0.3 seconds. That's A. And B says find the net torque on the fan as a function of time and find its value at t equals 3 seconds. Okay, the angular momentum, L equals I omega equals 2.5 kilograms meter squared times 40 radians per second cubed times t squared. That's the function. At t equals 3, we get 2.5 kilograms times meters squared times 4 radians per second cubed times 9 seconds squared. I put 3 in there and I squared it. And that's going to give me 900 kilograms meters squared over seconds. And one little mistake, this is 40. Yeah, 40. And so, yeah, I just verified it on my calculator, and that does indeed work out. All right, and similar to force and linear momentum, we've got tau equals dl dt. And so that's going to be equal to, what was, L was, let's see, 2.5 times 40 would be 100, right? 100 kg meter squared over second squared. And then differentiating that, you get 2t. So at t equals 3.0 seconds, we get tau at t equals 3 seconds. We get 100 kilograms meter squared over second squared times 2 times 3 seconds. And that's going to be giving me 600 newtons times meters. And there you go, that was 10.9. 10.10 says anyone can be a ballerina. Well, I beg to differ, but okay, I'll go with them. A physics professor stands at the center of a table with arms outstretched and a 5 kilogram dumbbell in each hand. So M equals 5.0 kg. He is set rotating about the vertical axis, making 1 revolution in 2 seconds. So it's 1 rev. That would be 0.5 rev per second, right? Yes. Find his angular velocity if he holds the dumbbells in order to his stomach. His moment of inertia without the dumbbells is 3 kilograms meters second squared. So I know dBs equals 3.0 kg meters squared. And with arms outstretched, and 2.2 kg meters squared with his hands at his stomach. So I no DB and no hands outstretched equals 2.2 kg times meters squared. The dumbbells are 1.0 meters from the axis initially and 0.2 meters at the end. What does that mean? Okay, I guess that means after he pulls them in. All right. Okay, and I'm supposed to find his angular velocity. Okay, so the total moment of inertia of the system, I system, equals I of the I professor plus IDB. And he's got an outstretched thing going on first, right? With a, let's see. Yeah, he's outstretched. And his dumbbells are, let's see, 1 meter from his axis initially and 2 meters at the end. So I initial is going to be equal to the 3.0 kg times meter squared plus 2, because you got 2 dumbbells and they're 5 kgs each, times 1.0 meter quantity squared. So this I initial is going to be equal to 13 kilograms times meter squared. 13 kg times meters squared. And we know omega initial, once again, is 0.5 rev per second. Okay, now I2, with his hands pulled in, I2, our final, or whatever you want to call it, is going to be equal to this guy, 2.2 kg times meter squared, plus 2 times 5.0 kg. And then what was that distance? 0.2 meters quantity squared. 0.2 meters quantity squared. And I2 is going to be equal to 2.6 kilograms times meters squared. All right, let me clean it up here and we'll continue. And we know there's no outside forces, so let me get a pen. L1 equals L2. So we've got, let's see, I1, which is 13 kg times meters squared, times 0.5 revs per second equals 2.6 kg times meters squared times omega final. And omega final is going to equal to 2.5. Wait a minute. Yeah, 2.5 revolutions per second. And if I want to know what that is, 2.5 rev per second times 2 pi r per 1 rev. And that's going to be equal to, let's see. Let's see. 2 pi radians, sorry, 2 pi radian. Oh, wait a minute, wait. I'm getting 5 pi radians per second. All right. Hi, everybody. This is example 1011. And it is called a rotational collision. It says, figure 1030 shows 2 discs, an engine flywheel, and a clutch plate attached to a transmission shaft. There are moments of inertia, or IA and IB. IA and IB, respectively. We put the dish together with forces acting on the axis so as not to apply any torque on either disc. The discs rub against each other and eventually reach a common angular speed omega. Derive an expression for omega. Okay, so this is the rotational equivalent of a perfectly inelastic collision. So we've got IA omega A plus IB omega B equals IA plus IB omega combined, if you will. All right, so that's basically it. That's the whole problem. Omega combined equals IA omega A plus IB omega B, where I is the moment of inertia, you guys, over IA plus IB. And that's that. Example 1012. And this is angular momentum in a crime bust. Fantastic, we put it to work. Okay, so we're looking at this diagram here. We're looking from the top of a door and what goes on here. A door of 1 meter wide and a mass of 15 kgs. Can rotate freely about a vertical axis through its hinges. A bullet with mass of 10 grams. This is door. And bullet. And a speed of 400 meters per second. Strikes the center of the door in a direction perpendicular to the plane of the door and embeds itself there. Find the door's angular speed. Is kinetic energy conserved? Okay, let's go ahead and do this. All right, we're going to solve this by conservation of angular momentum. So L before equals L after. So we're going to take the bullet and then the equals the bullet and the door system. So we've got L before equals the mass of the bullet times the velocity of the bullet times the distance to the hinge. So that's going to be equal to 0.010 kg, 0.10 kg times the velocity is 400 meters per second. And the distance to the hinge is 0.50 meters. And that's going to give us 2 kilograms meters squared over second. So this is a 2 kg meters squared divided by seconds. All right, let me get some board space. Now we need to know the moment of inertia of the door. So I of the door, and if you look that up on table 9.2, it's going to equal to mr squared over 3. That's going to be equal to 15 kg times 1.00 meter quantity squared divided by 3, and that's 5 kilograms times meter squared. Okay. All right, the moment of inertia of the bullet, we can just treat that as 1 point on the door. That's going to be equal to ml squared, where L is that distance from the hinge. So I of the bullet equals 0.010 kg, 0.010 kg times 0.50 meters, quantity squared. And that is going to give us 0.0025 kg meter squared. Okay, now we know from conservation of momentum, L before equals L after. So 2 kg meters squared over second equals I of the bullet plus I of the door. Remember, they're hooked together times omega of the system. So we've got that's going to equal to, let's see. I'll just figure, let me get some board space. Okay, I am actually solving for omega, so we're going to have omega equals 2 kilograms meters squared over seconds divided by I of the bullet plus I of the door. And that's going to be 2 kilograms meters squared over seconds divided by 5.0 kg times meters squared plus 0.0025 kg times meter squared. And that's going to be equal to 0.40 radians per second. All right, now I need to find the initial and final kinetic energies. So let me. All right, the initial kinetic energy of the bullet is 1/2 mv squared. So Ke initial equals 1/2 mv squared. And that's going to equal to 1/2 times 0.010 kg, 0.010 kg times 400 meters per second squared. 400 meters per second quantity squared, and that's going to be equal to 800 joules. And Ke after is rotational, so that's going to be equal to 1/2, and then I plus I. So what was that? 500. Okay, so 5.0025 kg times meters squared times 0. Omega squared, 0.40 radians per second quantity squared, and that's going to equal to 0.40 joules. So a lot of kinetic energy is lost there.